Hello everyone. My name is Kiran Patel, associated with LJ Institute of Engineering and Technology. So in this current video lecture series, we are studying subject of physics group 1. Till now in this chapter, properties of matter, we have learned the basics of stress strain, concepts of elasticity, time period of torsional pendulum, as well as we have discussed the twisting couple for a cylinder in solid and hollow cases. In previous videos, we have derived the equation of depression of cantilever beam in various three cases. So now, in this video, we will learn about viscosity and its measurement by a practical setup, that is Ostwald's Viscometer. So let's start with the first topic, that is viscosity. So here, viscosity is a property of fluid which describes the frictional resistance to the flow of fluid. We can say that viscosity measures the resistance of fluid to deform under shear stress. Here, you can see in the figure, the stationary layer which is steady is at lower portion, and if we move towards the upper portion, there is a maximum velocity layer. So we can say that the velocity of fluid increases as we are reaching upwards from downwards. So here, the viscous force is directly proportional to the area as well as velocity, and that force is inversely proportional to the distance. So here, if we combine all these three parameters, area, velocity and distance, then we can say that backward dragging force or viscous force is directly proportional to minus a v by x. So F is equals to eta minus ab by x, where we can say that eta stands for coefficient of viscosity. Here that equation is also simplified as F is equals to eta minus a dv by dx, because here we consider that change in velocity with respect to distance. So finally we have the equation of viscous force F is equals to eta a dv by dx, where eta stands for coefficient of viscosity and its unit is Newton into second upon meter square. So viscosity is a property of fluid which describes the frictional resistance to the flow of fluid. It also measures the resistance of fluid to deform under shear stress. So here we have derived the equation of the coefficient of viscosity. So now the next topic is measurement of viscosity. That setup is also known as Ostwald's Viscometer. So here you can see in the figure. Here first of all we will discuss the procedure behind this measurement of viscosity. So here, fill the viscometer with the liquid being examined through the tube to the slightly above the mark G. So you can see in the figure, we have to fill that tube through the liquid up to the mark G. Now place that tube vertically in the water bath and obtain the constant temperature. So this is the first step for the procedure. So we have to fill the viscometer through the liquid which is being examined through the tube slightly above the mark G. And then we have to place that tube vertically in the water bath and attain the constant temperature. Now, through developing pressure in the tube arm having bulb A, so you can see in the figure, we are discussing about the portion A. So here, if we apply pressure in the tube arm A such that liquid rises 5 mm above the mark C. So here you can see in the figure, if we apply the pressure in the tube, then liquid rises and it will reach up to the mark C. So this is the second step for that procedure. And now, after releasing the pressure, we have to measure the time t for the liquid to fall from the top edge of mark C to the lower edge of the mark D. So here we have to measure the time t for that liquid from top of the edge C to the edge D. So here we can say that we are considering the small section C. Now, repeat the same procedure 3 to 4 times to get the higher accuracy. Now, Ostwald Viscometer works on the principle of poised law for the capillary tube. As per this law, the rate of flow of liquid through the capillary rise having viscosity coefficient mu is given by capital V is equals to pi into V r raised to 4 upon 8 mu into L. In this equation, capital V is the rate of flow of liquid. P stands for pressure difference across the tube. R stands for radius of the tube. And L stands for length of capillary portion C. Here in this tube, we have considered that portion CD. That's why we are considering the length of that capillary portion C. So now, repeat the same procedure with the second liquid whose comparison is to be made having viscosity coefficient mu dash. And its rate of flow is capital V dash, and it is also given by capital V dash is equals to pi into V r raised to 4 upon 8 mu dash into L. So here we have two equations of the rate of flow of liquid. One is of V and second is of V dash. In both the equations, the pressure difference across the tube is same. Radius of tube is also same. And the length of that portion CD remains same. So here we can say that the coefficient of viscosity are different. Mu is in the case of capital V for the first liquid and mu dash is for the second case where that rate of flow of liquid is V dash. Since the pressure difference is directly proportional to the density of fluids, so we can replace the pressure difference with the density of fluid. So, taking the ratio of flow of rates of both the fluid, we get V upon V dash is equals to rho by rho dash, mu dash by mu, where rho stands for density of fluid. Now, due to the variation in pressure difference P and P dash, the flow rates V and V dash also varies during the flow of liquid. But their times for the flow of unit volume of the two liquid varies inversely to the V and V dash respectively. So here we can say that the total time T and T dash for traveling that portion CD, or we can say that distance CD will have the relation as V by V dash is equals to T by T dash. So finally, we can replace the above equation of V by V dash here. So finally, we have T by T dash equals to rho dash mu upon rho into mu dash. So from that equation, it is very clear that by knowing the density of fluid and by measuring the time to flow, the ratio of viscosities can be easily measured. So, here it is the measurement of viscosity by Ostwald Viscometer. Now, this is the last video of this chapter, properties of matter. So let's quickly revise the main topics, or we can say the important points of this chapter. So we will start with the first important point, that is stress-strain diagram. So now we all aware about stress and strain, and then we have discussed the types of elasticity, factors affecting elasticity, and various modulus of elasticity, which are Young's modulus, Bulls modulus, and shear modulus. Then we have discussed the time period of torsional pendulum and torsional rigidity. Also, we have derived the equation of work done in stretching a wire. Then, the important theory, that is twisting couple of cylinder. So, we have derived the equation of twisting couple of cylinder for two cases, hollow cylinder and solid cylinder. Now, in last video, we have discussed the derivation of depression of cantilever, which is fixed at one end and loaded at other end. And then, in today's video, we have derived the expression of viscosity and its measurement by Ostwald Viscometer. So that's it for today's session. Thanks for watching.